My name is Eric Millbrandt. I am the director of the Marine Laboratory at the Sanibel Captiva Conservation Foundation. Welcome to an Eastern oyster reef. Today we are right in front of the SCCF Marine Lab at the end of Tarpon Bay Road, and I wanted to tell you all a little bit about how we are monitoring the health of oyster reefs throughout the region. So you can see behind me is a nice reef standing on. All around there are live oysters, and growing on the reef is a mangrove, a red mangrove, which is a natural progression of Southwest Florida's geomorphology. As the barrier islands formed, there were oyster reefs that also formed, and eventually those oyster reefs are then colonized by mangroves. So often a lot of times the oyster reefs are somewhat hidden underneath mangrove islands, but as you look around the area, especially in the intertidal, you'll see eastern oyster reefs. Eastern oysters are highly threatened worldwide because of our interest in eating them, but these tiny and somewhat delicious bivalves are also a very important part of our ecosystem. They provide structure and habitat for small fish, and they also clean the water. They filter around 50 gallons per oyster per day. So if you think about a reef this size, thousands of animals filtering all day, that's a very good filtration and clearing property that happens at all the reefs. So what I'm going to do today is give you a little bit of insight as to how we monitor the health of oyster reefs. So one of the things that we use, we want to figure out how many oysters there are per square meter, per unit area. So I have a quadrat, and I'm going to harvest the oysters from the quadrat. It was randomly placed, and put them in the tray and measure the shell height of the oysters. So what we've done is we've created a grid on this reef of points, and what we're trying to do is figure out how many live oysters there are per unit area, in this case per square meter. This is not a square meter, this is a quarter square meter. We are subsampling within the meter. What we do is we place the quadrat and we harvest all the live oyster clusters and clumps from the quadrat. A lot of times we'll bring these back to the lab and measure them in the lab under controlled setting, but today we're just going to show you how we measure the height of oysters. So shell height is very similar to measuring shell height in all bivalve. Take the measurement between the umbo and the margin, and then we'll measure the height from the umbo to the margin. So this particular oyster is 46 millimeters. So by measuring all the shell heights within the sample, we then can calculate the number of live oysters per square meter. In addition, we can figure out the size structure. So how many small 1 year, 1.5 year, 2 year, and larger. Oysters don't typically live around here past 3 or 4 years. Occasionally you'll find a really large one. But I did find within the area that we're studying a tulip, a beautiful mollusk that actually will eat oysters. So there's lots of predators out here, and that's how we figure out how healthy the reef is looking at how many live animals there are per square meter. We really want to thank the Shell Club for the years of support of our organization and the many projects we're involved with. And oysters are a really important part of this ecosystem. We want to make sure that we have oysters for the future. So thank you to all the Shell Club volunteers, all the members. Thanks.
Hard clams are a very important part of seagrass ecosystems. In the past, hard clams were very abundant on the coast of Southwest Florida, and we know this because of evidence left behind by the Calusa Indians. The Calusa Indians used to consume and dispose of hard clam shells regularly and in large ceremonial events, and this ended up creating small, man-made formed islands, such as Mound Key and Estero Bay. When archaeologists dug the hard clams up from these islands, they discovered that these hard clams were dated back to 300 to 500 AD. So we know that hard clams have been established in this area for a very long time. In the 20th century, one of the world's largest hard clams fisheries was actually in 10,000 Islands here in southwest Florida. There was a 40-mile long, 5-mile wide swath of hard clams that existed in thriving seagrass meadows. However, by the mid-20th century, the hard clam fishery had collapsed due to overharvesting and changes in water quality. Hard clams can be found in seagrass ecosystems as large, white, round shells with prominent ridges. Hard clams have similar ecosystem roles as oysters in that they both filter phytoplankton from the water. Hard clams can help improve water quality by filtering out plankton from the water and decreasing competition for sunlight and nutrients with seagrass. They are also a really important part of the ecosystem because they take energy from the phytoplankton and transfer it up the food chain to higher trophic levels. There are two species of hard clams in southwest Florida. There's the northern hard clam, Mercenaria mercenaria, and the southern hard clam, Mercenaria campentiensis. Northern hard clam is the preferred species for aquaculture because it has a longer shelf life, so it's easier to sell to the marketplace. However, the southern hard clam is the native species, and its diversity here has been dwindling, especially with an increase in northern hard clam genetics throughout the area due to aquaculture. With our hard clam project, we hope to increase the number of southern hard clam species in this area and revitalize their population. And also, we hope to understand the effects that hard clam restoration has on the environment, such as does it change water quality and phytoplankton community structure. Since hard clam restoration hasn't been done yet in this area, our project is going to test to see how hard clam restoration is going to work using a small pilot study. This will help us determine what exactly is needed in order to scale up to larger ecosystem restoration efforts. Our study area is 900 meters squared, and we'll be putting 12,000 hard clams in this area, and we'll be monitoring them over the period of a year to see how they respond in terms of growth, survival, reproduction, and we'll also be looking at different parts of water quality such as nutrients and responses of the phytoplankton community. Since hard clams are filter feeders, we might expect to see some sort of change, like a decrease in the abundance of phytoplankton over the area where restoration was completed. Finally, I'd like to say thank you to the Shell Club for supporting this project and funding all research related to bivalves and gastropods and shells. I think what you guys are doing is really great, and I'm very excited to get started on this project. Thank you.